Okay, welcome back. I guess this is the 8th lecture out of 15, so we're more or less halfway. And I'm going to make a transition today into a subject that's related to where we've been, but very much related to where we're going in the rest of this course. And that is neutrinos. So today I'll pretty much cover introducing what neutrinos are, how they fit into where we've been talking, which is more particle physics, and some of the history today. And then the next few lectures we'll talk about some of the properties of neutrinos that I can't really do today, the fact that they do this, they actually have mass, which is an important feature, and they change their identity in certain ways, and their role in astrophysics and cosmology. So we'll see that this subject actually crosses a lot of disciplines. We've looked at the standard model, everything in here, plus the Higgs, which isn't shown in this plot right here, and we've gone through the quark model, for example, and understood the different quarks, the up-down quark, the mystery, as I described it, that we don't really know why there's a mere 3 versions of each one. That's one of the puzzles left for us to understand someday in the future, why there's 3 families of quarks and leptons. But we started with the up and down, and then we've been through the discoveries and the features of the charm and the strange and the bottom. And as I pointed out, the particular mystery of why the top is so heavy compared to the other quarks. We've also gone through the force carriers, the strong force, which is carried, as we saw, through this, explained through a property which we talked about called quantum chromodynamics. Basically, is described here by the force carrier, the gluon, the gamma ray for the gamma for electromagnetic interactions, and the weak interaction. Last time we showed you the discovery of the Z and the W boson, which described the weak force. Gravity's, of course, much weaker than any of these. And the one part of this diagram, and then we also talked about the Higgs, which is responsible for mass. The one part of this diagram that we only alluded to where it came to be described is neutrinos. And I saved that because of the fact that they're not only kind of mysterious, but they touch so many other fields and are pretty much a subject on their own. So we've pretty much filled out everything around this. We can talk about neutrinos from the point of view of several of the things that I've shown you before, some conservation laws and so forth. And as I said, we're going to describe both their mysterious features and their role in adjacent fields, especially astrophysics and cosmology. So let me start by showing you there's a puzzle from the very beginning. We can talk about weak decays, for example, and I've drawn on here the decay of a neutron. So a neutron decays into a proton, an electron, and an electron neutrino. And on the top, I just show it as a bunch of pictures, but here I've shown it the way I did last time as quarks, where what's happening is somehow inside the nucleon, one of the quarks is changing identity in order to make a proton from a down quark to an up quark. So that we have to understand and describe if we're going to describe the decay of a neutron. And then in the final state, it makes an electron and a neutrino. So a neutron makes a proton, an electron, and a neutrino. It has a lifetime that's seconds, 888 seconds, which is long compared to all the elementary particles that we talked about, but this definitely is something that's measured. And people work very hard at describing exactly the decay itself, it's a difficult subject to try to understand. What I want to point out here is that it immediately creates some puzzles. I draw those diagrams, but immediately there's an issue. And that is, we've got a picture here where we somehow have to change an up quark to a down quark to an up quark, rather. And but we've talked about the quark model for weeks, and those quarks are supposed to be singular and unique. So what does it mean for it to change its identity inside of a proton? So we have a down quark that gives up an up quark, and somehow that doesn't fit the whole picture that I've drawn for the last weeks. In the process, of course, there's the weakly decaying products, the electron and neutrino, that come out. But if this is true, then we have these lifetimes that are strange. The neutron has a lifetime, as I said, of 888 seconds, while the proton, the other companion particle, has a lifetime that's incredibly long. The lifetime is something like 10 to the 23 times or 10 to the 24 times the lifetime of the whole universe. And it's at least 10 to the 35 seconds. And yet we have a neutron that has a lifetime that's tangible. It's 880 seconds. So that's kind of a puzzle that we have to understand. Thirdly, many of the elements of the periodic table are actually very stable. And yet, many of them have many neutrons. So why don't we have conversions of those neutrons into something that has protons in the same way that happened here inside of all these nuclei, which is something else that's kind of puzzling on first order. So there's a whole bunch of puzzles that happen almost immediately when we start talking about these decays. But let's step back first and just talk about the neutrinos and what some of the features are and where they come about in nature, and then we'll start trying to work through what the properties are of the neutrinos and how they affect the science. So just the scale of things first to remind you. A virus, shown in the top, is pretty big. It's about 10 to the minus 7 meters. And then we move into the physics, and we talk about molecules, which are about 10 to the minus 9 meters. The atom itself is 10 to the minus 10 meters. To make the nucleus of particles, we're down to 10 to the minus 14 meters. The proton is 10 to the minus 15 meters, and that's the size that we study on very large accelerators, for example. And quarks themselves, we don't know. We treat them like they're points, but we know at least that they're smaller than, say, 10 to the minus 18 meters. And so that's where we start. Now, neutrinos themselves are first fundamental particles. I showed them to you on the chart, and everything we know would make them fundamental. There are a lot of them. There's something like 10 to the 12th neutrinos every second that go through everything, your life, yourself, and they're going through you. And those are just the ones that I know about that are coming from the sun. So the process of the sun, which we've mentioned, happens through nuclear fusion. And in the nuclear fusion process, the burning of the sun, it creates secondaries that decay and make neutrinos. Neutrinos come from the sun. We'll talk about the detection of those neutrinos. I forget whether I do it today or next time. But there's a lot of them. They're pervasive. 10 to the 12th of them go through us every second. If we wanted to actually create an interaction with neutrinos, we need something like 10 to the 13 kilograms of lead. So mostly they go through you and do nothing at all. There are billions of these neutrinos for each atom that's in the universe. There's 3 10 to the 8th of them in every cubic meter. So they're important. They fit everywhere. Their sheer number basically tells us they're important. And they have properties. For example, they come in one particular way that they spin. They spin left-handed, what we call left-handed chirality. So these are the general features of neutrinos. They have absolute, predictable, or explainable features. Each neutrino, I'll show you how that's determined, are spinning when they go at high velocity, which they do, the speed of light. They tend to be like a screw going left-handed. Not tend to be, they are. And they have this very tiny interaction. So let's pursue it a little bit more. So first, they're what I call left-handed. In the standard model, which we talked about over the last weeks, in the minimal case of the standard model, they're massless. But we're going to find they have mass. I'll show you. That mass is not explained in the way I described mass to you before. It's a mystery, or let's say separate from that. They're not produced in a known way from the Higgs mechanism that we talked about. They're just there. They're the only fermion, that's the particles that have spin a half, in the standard model that are neutral in charge. I'll explain that we don't know whether they have their own antiparticle or they have a distinct antiparticle that's different from the particle themselves, and that we call either different theoretical explanations of what that means, whether they're Majorana or Dirac fermions. And they come from a lot of different sources, and I'll try to cover some of the physics in many of those. They come from the sun, as I mentioned, is a very prolific source. And that describes to us something about how the sun works, the nuclear fusion process. And from the fact that the sun has certain temperature, certain age, and works by the nuclear fusion process, we can predict quite accurately how many neutrinos and what kind of neutrinos are emitted from the sun. And that's resulted in a puzzle for a while, and then an understanding that neutrinos actually have both mass and can change their identity in time, what we call oscillations of neutrinos, neutrino oscillations. We also will talk a little bit about relic neutrinos. What I mean by that is neutrinos that come actually from the early universe. And in principle, if we could detect those, we can find out what we can't do with photons, and that is about the early universe in the first seconds of its life. Unfortunately, they're very difficult to detect, and they've never been detected directly. And that's because in making them in the early universe, they've had a lot of time to what we call thermalize, which means they're very, very low energy. And it turns out, as I'll show you, that the interaction cross-section of neutrinos is a function of its energy. So at very, very low energies, it's very hard to detect those, although people are trying, and potentially it would be a very wonderful way to directly study the universe in its very early moments. That's also going to be true of gravitational waves when I talk about them, even at earlier times, the very first instance. In both cases, we don't know how to do it yet, so it's for the future. In the case of neutrinos, there's people trying to do it now. In the case of gravitational waves, I think they'll probably be detected, but not in the next year or two. And I'll describe what those problems are when we come to gravitational waves. Another way that neutrinos are created and is by just because it's not so different from what we talk about in the sun in the way it works, and that's in nuclear reactors. And some of the experiments I'll talk about will come from nuclear reactors because they're a very good source of neutrinos that we can study at low energies. Then we have neutrinos that are made on accelerators. I showed you that very briefly before when we talked about, I didn't talk about the neutrinos, but I talked about particles that were unstable and gave neutrinos in their final state that are made on particle accelerators. Finally, neutrinos come from the Earth itself by processes that happen in the Earth, by radioactive decay. They're a product of radioactive decay, which I'll show today as much of the early history of what we know about neutrinos. And of course, in our bodies, we have radioactive decay, so we actually produce a very large number of neutrinos ourselves every day and every second. So first, as I said, studying neutrinos from the Big Bang would be great. There's a lot of them. There's 330 neutrinos per cubic centimeter all the time coming from the Big Bang. But their energy is extremely low, 4 × 10⁻⁴ eV. And they were decoupled from what happened in the Big Bang at a very early stage. If we could detect them, then it's a picture back then. The only way we take a picture now, which I'll show in the future, is by looking at what we call the cosmic microwave background. And that's looking at photons as far back as we can see them. But we can't observe them earlier than about 300,000 years after the Big Bang itself, because they were too dense before then, and one can't see the gamma rays that come from then. So everything we know about the early universe comes in directly because we can't go back beyond 400,000 years. If we could do neutrinos, then we could go back to something like seconds or a minute after the Big Bang itself. Neutrinos that come from the sun come because the sun itself works by the nuclear reaction, essentially the fusion reaction. And they tend to be more energetic, not high energy, but energetic, something like 1/10 of an MeV, up to 20 MeV. And much work has been done, and I'm going to show a lot of experiments that look first for the neutrinos that came from the sun to verify that the sun really worked by the nuclear fusion process. And then secondly, the puzzle that the number that we're seeing were not what was predicted. And that has been the evidence that led us to this understanding that neutrinos change identity one to another. A third source is the explosion of stars, or the implosion of stars, and that's what's called a supernova, what happens at the end of the lifetime of a star, after it's burned up all its nuclear fuel. Then gravity becomes more important than the outward force from the nuclear fusion process, and a star collapses. When it collapses, there's a huge amount of energy involved. I write down here 10⁵ ergs. And those neutrinos are a little higher energy. They're something like 10 to 30 MeV, and they come out in a burst of energy as the collapse happens. So again, just to look at the whole picture, every second then, our body receives something like 1 trillion neutrinos from the sun, 50 billion neutrinos from just natural radioactivity from the Earth, something like 10 to 100 billion neutrinos from all the nuclear plants that are in the world. And our body itself produces neutrinos. We have something of the order of 20 milligrams of potassium-40, and potassium-40 is unstable. It decays by radioactive decay, beta decay, and we emit through just the potassium in our body about 340 million neutrinos every day. You'll see we emit, we receive. Neutrinos are everywhere. And they leave our body, of course, everything is so light, a neutrino, even though it has a little bit of mass, that it's essentially going at the speed of light. And they don't do very much. So what I wrote here is, you can see how many zeros, how many people it would go through before it did anything. So these are really pretty mysterious issues. So I'm going to kind of go through a lot of these areas one at a time, but maybe a little bit historically first, to talk about how we know what we know about neutrinos. So first, there's a lot of neutrinos around. I've told you that. They are the second most abundant particle in the universe. The most abundant are the gamma rays in cosmic microwave background, the photons that are seen. problem is that the neutrinos, as I said, are so low energy that despite the fact that they're so abundant, they're very difficult, at the present time impossible, maybe not impossible forever, to detect. So I've shown this once before, but we're going to see this more and more as I move into especially cosmology and astrophysics. But this is kind of one picture of the expansion of the universe, starting at the left side from the Big Bang itself, back here. It this size this way is how big it is. So it expanded very fast early. That was something that was learned and comes about empirically, and there's theoretical explanations that people use, but it's very much established that in the early universe there was something we call inflation. What that means is it expanded very rapidly, like inflation in the early universe. So that's shown pictorially here by at the very early times it got big very quickly. Then at 300,000 years, which I talked about, we start having a form of the universe where we can start to look at it even in the present time. That's what we call the cosmic microwave background. Not much happened for a while. I'll show you that. And then when we get to, we'll do this in detail when we get to the cosmology. But then we started forming the first stars at 400 million years, eventually developed galaxies and planets. And you'll notice in this that we're subtle enough that this, again, goes outward. And that's because there's a known speed up in the expansion of the universe, which is one of the big discoveries and puzzles of the recent years. Altogether, since the front, we know by other measurements, which I'll go through later, that the whole age of the universe is just about 14 billion years. So that's an overall picture, which I'll show a couple different ways. So this is just another picture of the same thing, kind of looking at it from the standpoint of the formation of particles and then galaxies and so forth. So this is showing the same thing as I showed before, but just to see what the universe looked like at different times as we moved out. So this is now. This is, of course, the beginning. We started and went a little ways, then it had inflation and got bigger. And at the early times we started at this point to start to be able to make the fundamental particles. And then a little bit later, we think we made dark matter relics. Eventually we get to where we can make, have nucleosynthesis and make heavier particles. Eventually, they're shown here. Eventually they can form into matter, and then we get eventually galaxies and so forth. So the history of the universe is something that I'll try to trace for you, at least the main elements, reasons why we think it looks like this. But I'll say that the puzzle of what happened before 300,000 years, which I show here, way out here, back here, is determined very indirectly because we don't have any probes experimentally really that go back that far. So I'll show you how that happens when we get to cosmology early next year. Let me skip this. This is just some details of what we know, which I'm going to skip for now. Relic neutrinos then influence several cosmological aspects. The relic neutrinos are the ones that I said come from the very, very early universe, and they affect things in cosmology. First, the first is how primordial nucleosynthesis worked. That's how we started making particles. And that happened when the temperature was something like an MeV at high temperature and things cooled down. The cosmic microwave background is our biggest and most detailed experimental observatory, if you want, or observation of what the early universe looks like. And that's still it's something that's developed over the last 20 years. It's probably the most important tool that's made cosmology into a actual field that isn't just conjecture, but has real constraints that come from measurements, which is only in the last 20 years or so. And the details of it tell us a tremendous amount, which we'll see. The relic neutrinos actually affect what it looks like, and I'll show that to you when I'm talking about neutrinos, and later we'll come to understanding this whole picture. Then we have areas that we look at specially because they tell you something about formations and certain things in cosmology, like what we call large-scale structures in the universe. And again, they're affected by neutrinos. So I'll preview that as we talk about neutrinos. As I said, the biggest piece of information we have comes from the cosmic microwave background. Ideally, when we look at this in detail, we know it's affected by neutrinos. For example, what I show here is just a modeling of how neutrinos affect the structure this measure. This is the influence on what we call the small scale structure of the universe. Different masses, if the mass of a neutrino was 1 eV or 0 or 7 eV or 4 eV, we don't know yet at this scale empirically. We think it's very small, but we're just getting the technology, which I'll show in a few weeks, to actually try to find out what the real neutrino mass is. So far, we know something about the differences in masses between the neutrinos that have mass, but we actually don't know what the masses themselves are yet. And the mass of the neutrino affects the structure astrophysically. So I'm showing this kind of as a preview. This, for example, shows the influence of the neutrino mass on what we call the matter-power distribution we get of observations in the universe. And you'll see on the right-hand side, they're not distinguished, that there's a dotted line and a solid line, and that's the difference between two different masses of the neutrino. I think, I don't remember, 1 eV, I think. So the dashed line corresponds to 1 eV, the solid line is no mass, and basically we can't measure it this way, but I show it to illustrate that, again, the neutrino affects a lot of what we try to do and understand about astrophysics and especially cosmology. Okay, so why don't we just measure this cosmic microwave background, but maybe call it cosmic neutrino background, which would get us back to a few seconds from the early universe. There's attempts to develop the technology to do this. The challenge is that the relic neutrinos have what we call thermalized. They were made so early in the universe that by the time they've propagated, they've reduced to kind of thermal temperatures. And that means they're very, very slow, non-relativistic. And being non-relativistic, it turns out that they interact even less. So I told you about all these neutrinos and how hard it is to detect them, how mysterious they are in the sense that there's so many, but we don't see them do very much. The great desire to see these very early ones is tempered by them being even harder to detect because of the fact that they've slowed down, they're non-relativistic, and they interact even more. Again, I show kind of how the neutrinos might affect the structure that we look at in the galaxies. And there are instruments that are being made now. I show a picture of what's called LSST, or the Large Synoptic Survey Telescope, which will measure distributions, we think, by doing them very systematically. It'll take a picture of much of the southern sky with great accuracy and great depth. I don't remember exactly the rate, but a few times every day, and over a period of like 10 years to see the changes, the transient changes, but also to map it and be able to do things like this. This has required incredibly actually a marriage between technology built for accelerators and technology that you use to do astronomy. And so it's a big, ambitious project being presently installed in Chile and will be operational despite what it says here, because I took an old picture in 2022. So now I want to go back and talk about kind of how we know what we know about neutrinos, starting from the beginning. Where did we find out that neutrinos existed at all, and how did we get to where we now are going to do modern physics? So I'm going to go back now and talk about some history and build ourselves up to getting the first features of neutrinos before I do the modern questions that I've kind of previewed for you. First, just going way, way back, we can start with Becquerel, who discovered natural radioactivity. And by putting fluorescent materials like uranium ore on a desktop, and noticed that exposed film that was in drawers below could see a shadow. And that was radioactivity, of course. The early history then probably starts with J.J. Thomson, who discovered the electron using a cathode ray tube. I pointed out to you that the cathode ray tube, as primitive as it was then, was the primary way that we viewed television until just a few years ago. So it's one device that's lasted almost about 100 years, include for almost all of us. And in many ways, although now we use digital televisions, we basically have used a cathode ray tube one way or another for a long time. It was responsible, and I showed you this, for the discovery of the electron. So he demonstrated that cathode rays were negatively charged, and he also studied positively charged particles using neon gas. So that's where we started. And then Pierre and Marie Curie discovered beta rays, or electrons, using a source, a collimator, and seeing that there were alphas, gammas, and beta rays. And that's where we were in the early 1900s. Okay, then we came to the first history, which started to need something that wasn't explained. And in 1914, Lisa Meitner, Otto Hahn, and Chadwick studied the decay of potassium-40 into calcium-40 and an electron, and got a distribution that's shown here. Okay, and the early puzzle immediately was, if this involved what we thought, which is a two-body decay, which I've shown here. If this involves a two-body decay, then I can calculate the energy of each of the particles, and they should come out at a unique energy with some error for what the different masses are. So the final products within the measuring error should be a unique energy. But instead, we get a spectrum. So the early puzzle, which was a puzzle during the period of the 1910s to 1930s, was beta decay, what we call beta decay. And so what I show here is rhodium decaying to palladium and a beta particle. And it gives this continuous spectrum, which was observed. That was a big problem in physics to explain. And in fact, the explanation was unclear completely. And prominent physicists had different approaches to it. For example, Niels Bohr, one of the most important physicists of the 20th century, was willing to explain this by abandoning the laws of conservation of energy. Somehow in the process, you can get this distribution because energy is not conserved between the initial state and the final state. While, for example, Einstein was firm that conservation of energy was a concept that was firm and he believed. So basically, there was a puzzle at this point into the 1930s, even though this was seen sometime before this. And For the first thing that maybe was relevant is that it was determined by something like 1927 or 1930 that there wasn't somehow gamma rays that were getting away that you didn't see that were taking away the energy. So that was disproven by about 1930. And then Wolfgang Pauli proposed the solution. And he proposed a solution in a famous letter that was written in December 4th, 1930. And of course, translated here, and I'll read it. Dear radioactive ladies and gentlemen, I've hit upon a desperate remedy to save the law of conservation of energy. Namely, the possibility that there exists in the nuclei electrically neutral particles that I call neutrons. At the time, people just thought the nucleus was just a mass that were made of the protons and electrons somehow making up the. So he said there was electrically neutral particles that I call neutrons. Notice the word neutrons. I agree that my remedy could seem incredible, but only the one who dare can win. Doing something radical. And unfortunately, he can't appear in person at whatever meeting they were talking about, since he has he's indispensable at a ball in Zurich. And that was a very famous letter. The final solution to what's happened, I hint at you at the top on the left-hand side. So notice that this was 1930, and that was actually before we discovered the neutron itself. So there's some confusion here in the wording that I'll explain. So Pauli's idea then was that the beta decay itself is really a three-body decay, and that's why you don't get a sharp peak. And so the nucleus decays into another nucleus, plus an electron, plus what he called the neutron. The neutron carries away some of the energy that's released in the decay. And so the amount that it can carry away can vary, and therefore what you measure is a spectrum that we saw. And now, if that were true, momentum can be conserved. So inventing a new particle was not, at that time, an accepted idea that seems to be popular in modern times during my lifetime as a physicist, a popular way to solve problems in physics is to, and often been right, to propose some new particle that we haven't seen. In the last lectures, we've talked about two particles like that, the Higgs boson, which was basically invented as part of the explanation for where mass comes from. And so that was proposed. And I also told you about a particle that's been proposed, but with a lot of strong belief that it was going to be there, but people haven't found, which is called supersymmetric particles. So we've talked about both of those. But if we project back to 1930, it was pretty radical to propose that another particle was the reason we were getting this explanation. And in fact, a very famous and important physicist, Sir Arthur Eddington, said that he didn't believe in this explanation of this ambiguous words I'll explain in a minute, in neutrinos. Dare I say that experimental physicists will not have sufficient ingenuity to make neutrinos. I'll talk in a few minutes after the break about how we first discovered neutrinos. So that's the history there. And then, very quickly, by 1932, to solve this problem of nomenclature, but actually to solve a physics problem, James Chadwick discovered the neutron. So let me throw that in. It's not the story of the neutrinos, but it happened in 1932. So before that, we only knew about protons. We thought the nucleus was made out of protons and electrons. And then Chadwick came along and he did this experiment here. He used a polonium source that made alpha rays, alpha particles. And those alpha particles were then incident on a beryllium target. And out of the beryllium target, some unknown radiation happened, were neutrons, but he didn't know that. He used some paraffin, and out of the paraffin they converted and made protons, which he detected. And basically, after observing them in an ionization chamber and all the checks, this became the proof or the existence of neutral particles like the proton, the neutron. So the discovery of the neutron was made by this experiment by Chadwick. And so following that, we then had to rename the particle that I was been talking about, the neutrino, and that was done by Fermi. Of course, neutrino in Italian we know means little neutral one, and that was a very clever name to call it a neutrino because it doesn't specify whether it's like the gamma ray and has zero mass or in fact has tiny mass. Just a little neutral one. So we know it could have tiny mass or zero mass. So in some ways it was prophetic of the fact that we have been spent tens of years not knowing whether it had any mass at all and are still working on the problem of neutrino mass, which I'll come to. So Fermi in 1933, this is just a year after Chadwick, introduced his scheme for what would be, for example, neutron decay, which I showed a few minutes ago, into a proton, an electron, and a neutrino. And he treated this neutrino as if it existed, and it is a spin-a-half particle, a fermion, we talked about earlier. And by conservation of angular momentum, the neutrino has to be a fermion, and it obeys, if we talk about the process quantum mechanically, the Dirac equation. Fermi then developed a formalism parallel to the equations that you use for the electromagnetic interaction and an intermediate propagator, an interaction, which he called GF. And so that's shown here, that we have basically in a modern description in quantum field theory, we usually show in lowest order a picture like I show in the upper right-hand corner. And this would be the force carrier of the weak interaction, the Z or the W boson. And I showed you the discovery of those in the last lecture. The first theory on weak interactions that Fermi introduced wasn't quite as sophisticated yet. But he saw that the neutron decayed into a proton, an electron, and an antineutrino. And he drew it this way, what we called a 4-Fermi interaction. And this was some form of quasi-electric elastic scattering. And one could then develop a theoretical way to do the calculations. And this was beta decay theory, where he was able to write down a way to calculate these by having a baryon current, a lepton current, and a coupling constant, which I write down here. And this was the concept that was introduced until we introduced what we call currents, which was years later by Feynman and Gell-Mann. So this was the scheme by which weak interactions were studied and interpreted from the 1930s until the 1950s. And Fermi concluded that the differences in lifetimes of various elements was basically due to the differences in phase space that they had to decay. So the final state of an electron and neutrino are very light compared to the nucleon, and so they don't contribute very much to the amount of phase space that's there. And you can calculate then the strength of this interaction if you go through it. And I write it down here in units of GeV to the -2. And what was missing then, of course, is that there's a whole picture here, but is there really, this is 1930s, is there really this invisible particle that hadn't been seen? So he could calculate what the particle was. It was believed that the cross-section for this was so small, I've written down here, the cross-section something like 10 to the minus 48 meters squared by using this same formalism to calculate it. And so the general belief was it would be impossible to detect, but nevertheless it was detected in 1956 by Cowan and Linus. And I'll show you that in just a minute. And you could look at all the other beta decay using the same mechanisms. So I've shown several examples here. Beta decay is the top one, but I could also look at K capture and so forth. And this general picture of weak interactions is what preceded. And during the same year, I think the same year, or about the same year, Fermi did an experiment which discovered artificial radioactivity, which is what he won the Nobel Prize for. When he went off to get the Nobel Prize, he proceeded to continue to the US, and that's when he immigrated to the US in 1938. Okay, so in modern days, we look at the weak interaction or the decay of the neutron a little bit differently. So we have spectator quarks, as we call it, and we have a decay that looks more like this. You doing that in the 1930s, the cross-section I've written here, and this began the long quest to see if there was a neutrino and whether it could be detected. And in fact, Fermi himself made an offer that he'd buy a case of champagne to whoever could first detect the neutrino. Okay, so let's talk about detecting the neutrino then, which is the next piece of history, and then we knew that the neutrino actually existed. And it's kind of an interesting story. Making neutrinos, we make them by beta decay. So a neutron decays and makes an electron neutrino, for example. And we said the necessity comes from conservation of energy and momentum. And for the sake of conserving something that I showed you when we talked about particles, and that is lepton number conservation, the electron has to be accompanied not by a neutrino, but by an anti-neutrino. So what we know is if we have this decay, we're going to have an what we call now an electron neutrino. So that's what we're going to look for. And the mass limit itself can be estimated from precision measurements of beta decay, and we just knew at this stage that they were light. And the best results for the decay itself, and I'm going to show you that that's the way we have the best experiments directly now to see the neutrino mass, where we only have a limit on what the lightest neutrino weighs, is to look at the decay of tritium itself. And the most ambitious experiment today, which is being done as we're sitting here, is using tritium. And the mass is actually, the limit is a little better than this now, but basically the limit for the lightest one is really small if you think of the mass of the other elementary particles. It's less than a couple of eV, probably less than an eV by the more recent limits. Okay, so the challenge of detecting neutrinos. So let me just graphically show it here. If I have a bunch of gamma rays and I run it into water, what does it do? Many of them interact. I can have 3 centimeters of water and half of them will interact if my gamma rays are, say, 1 GeV. So it's easy to make gamma rays interact. Now we have the same thing, 1 GeV neutrinos, and I put some water up. How much water does it take to have one of these neutrinos interact? About 10 to the 9th kilometers of water. So they don't interact very easily. So that's the first thing as a puzzle. The neutrinos from the fusion process in the sun are typically 3 MeV, not GeVs. And the cross-section is much smaller. It goes as the energy. And so they typically travel something like 53 light years in water before they'll interact. A 3 MeV electron goes a few centimeters. So that's the problem we have if we want to detect neutrinos. And I explained the sketch already. So how can we then detect these neutrinos as fundamental particles? And this existed until about the 1950s. What we want to do is see that the neutrinos, when they interact, do something that we can detect. So for example, an electromagnetic interaction in material, we kick an electron away from the atom, and then we can detect their deflection and its ionization. For neutrinos, we don't have an electric charge, and they only interact weakly, and we can only detect the byproducts of their weak interactions, so we don't have the ability to do this. So the challenge then is how to detect, or at this point, how to discover the neutrinos. And Clyde Cowan and Fred Reines took on this problem. And at that time, they were at the Los Alamos National Laboratory. You realize that's the laboratory where they developed the atomic bomb, and you'll see that affected their thinking. They conceived a plan to detect these neutrinos experimentally, but their idea was to use the enormous flux of neutrinos that would be produced in the tests which were being done at that time of hydrogen bombs or atomic bombs. And they even designed an apparatus that might be able to do that. And it was to be installed at the test site to detect neutrinos. Well enough shielded so it would survive and they could detect neutrinos. This was a serious proposal. So they, however, were dissuaded from this crazy scheme by the leaders of Los Alamos Physics Division, especially someone named Kellogg, and they were pointed that maybe they could do the same thing on a nuclear reactor instead of a nuclear explosion. And in fact, that's the way they were finally detected. So the first experiments themselves were conducted, and I'll show you what that looked like in a minute, at the Hanford site in Washington State, where they got some results, but they were somewhat ambiguous. And they did a second, better shielded experiment in the Savannah River plant, another reactor in South Carolina, where they made the final detection. So let's see some of this. So first, this is from their little paper, which I have, their proposal to actually detect neutrinos from a nuclear explosion test that would be done at some time there by putting these detectors, which were put underground themselves, a kind of trap door and a way to actually detect that the bomb went off, and then to detect the neutrinos underground that came from this detection. And then, of course, they go off and win their Nobel Prize. Instead, they did it on a reactor, and this was done finally in 1956. And the reactor is a fission reactor using U-235. And doing that, they then put outside of the reactor liquid scintillator. That's a liquid that has, when a neutrino would interact, makes a product that ionizes the liquid. When it ionizes the liquid, that gives off, by energy loss, some photons, and the photons get detected. And so the process is kind of shown here, but that's the general idea. They did this, as I said, first at Hanford. The result was somewhat ambiguous, and they did it again at Savannah River. They tested then whether they actually saw anything by doing it with the reactor on and the reactor off. And they got a result, which you can see here, of 2.88 excess with the reactor on, minus the reactor off. And although there was a background, this was enough to actually convince themselves and others that they saw this reaction. They call this project poltergeist, which is a word that's been used a lot to describe ghostly-like reactions. And I've shown here just the apparatus itself is shown here. And the actual reaction that they see when the neutrino interacts and what they detect in this liquid, which is really cleaning fluid that they use. And so the experiment, as I say, was attempted in Hanford, and they repeated it at Savannah River in 1955, and that was the discovery of the neutrino. I probably should take a break now, so let's take a break and then we'll continue.